Presto is a low-latency SQL language for interactive analysis. My guest, Christopher Berner, works on the Presto team at Facebook. Chris, welcome to Software Engineering Daily.
Thank you.
What is Presto?
Well, like you said, Presto is a low-latency SQL query engine, and importantly, it's distributed. So we use it here for a lot of interactive analytics in our data warehouse, as well as a number of other companies in the Valley, Netflix being one of the prominent contributors.
And I think Airbnb and Dropbox are also consumers of the product.
Yep.
Who are the end users? Are they data scientists doing ad hoc queries, or are they engineers that are programming Presto queries into their software?
It's a variety of people. So Presto is very flexible. One of the main areas of flexibility is that you can connect it to different data stores. So you can connect it to your data that's in HDFS and use it in the same way that you would use Hive. Of course, it would be a lot faster than Hive because it was designed for low latency. But you could also connect it to, say, your sharded MySQL deployment or your sharded Postgres deployment. You could connect it to your proprietary data store. So it can be used for both analytics for people that are doing reporting, or it could also be used by software engineers for people that are building user-facing products.
Could you provide a contrast between, before we get into a discussion of Presto, could you define a contrast between how HDFS works and how like a sharded MySQL database would work, for example?
Yeah, for sure. So HDFS stores its data on local disks on each data node, and then clients that connect pick a data node. And so all of those data nodes form a distributed file system. It includes features like replication, so that if one of the nodes dies, there's still another copy of the data somewhere else. But basically, it's just a distributed file system. And then Hive, which is built on top of Hadoop, stores all of its data in HDFS using a particular hierarchy of data, and it also uses the metastore to locate where different pieces of a table are. Whereas a sharded MySQL deployment is built on top of MySQL rather than directly on top of a distributed file system. And so typically the way that you would build a sharded MySQL deployment is you pick some key, for example, user ID, and then you hash that key and distribute your data so that each user's data ends up on a different MySQL instance.
In the past, Facebook primarily used Hive for its distributed queries. Describe Hive in a little more detail.
Yeah, so like I was saying, Hive's built on top of Hadoop. And so specifically, Hive is mainly a translation layer and then runtime for HQL, that being the Hive query language.
And why didn't it work for Facebook?
Well, it actually does work, and we continue to use it extensively. But specifically for interactive analytics, it has a number of drawbacks, the main drawback being latency. And that sort of comes from the design. The first step in running a Hive query is that you translate it from HQL into a Hadoop MapReduce job. And then you distribute the jars and the configuration to your Hadoop cluster, which then processes it. All of this, including the Hadoop framework, has a fair bit of latency, and so it's difficult to run queries in, under a minute or something like that, depending on your cluster. Presto, however, was designed for very low latency, so you can easily run queries in a second. And so for interactive analytics, where you may run one query, then tweak it a little bit, run it again, it's very important to have that low latency.
Yeah, so there's a good quote I saw about Presto, about Hive, actually. A good day is when I can run 6 Hive queries. This was from a Facebook engineer. So as I understand, the bottleneck in Hive is that there's a Hive query gets broken up into a series of MapReduce jobs, and and I promise we're going to get into the discussion of the engineering on Presto, but maybe you could describe in a little more detail, what does Hive do when it and you did mention some with the jars, but how does Hive translate just a high level SQL query into a series of MapReduce jobs?
Yeah, for sure. So basically, the sequence of events when you submit a Hive query is that it parses your query and then comes up with a plan. And that plan, because it needs to run on MapReduce, needs to be a series of map and reduce jobs. And so, for example, let's say you were doing a join between two tables and then a group by. So it would start out with a scan of both tables and then a join, and then it would have a group by, and in between each of those, you would need to shuffle the data. So it would probably be something like a table scan followed by a hash, and that would all run in one map job. And then on the other side, you would have a table scan and a join, and that would be a different MapReduce job. And one of the main areas of latency is that in Hadoop, every stage between map and reduce involves an intermediate write of all of the data back to HDFS to have fault tolerance, which is great if you're running some enormous job that's going to run for the entire day. But frequently, people that are submitting SQL queries are hoping to get their results back in seconds or single-digit minutes. And so having all of that fault tolerance actually increases a lot of latency without helping you very much, because the chances of your query failing in a few seconds are very low. And so that checkpointing between every MapReduce stage is where a lot of Hive's latency comes from.
From the Presto documentation, it says, quote, Presto allows querying data where it lives, including Hive, Cassandra, relational databases, or even proprietary data stores, end quote. Describe this statement in more detail.
Yeah, exactly. So that's some of the flexibility that I was talking about, where you can connect it to different data stores, like Sharded MySQL or Hive. And so the way that works is that there's a connector API. And as long as you implement that interface, it can read data from wherever you have your data stored. So many people use the connector, which it ships with, to connect to HDFS and read Hive data. We also ship a Cassandra connector, and that allows you to query data that's in your Cassandra store, and then query it in Presto. And similarly, if you had a proprietary data store, you could implement this connector interface, which typically takes you a couple thousand lines of Java code, I would guess. I've written a couple of these connectors myself, and they're pretty simple. And then it would allow you to run SQL queries over whatever proprietary data store you had.
So let's go through an example query and discuss how Presto's backend will process that query. So a user submits a query through his client, and the client communicates with the coordinator, and then the coordinator talks to the workers. Describe the interaction between the client, the coordinator, and the workers.
Yeah, sure. So the client can be pretty much anything, because we have a REST interface. So common clients to use are the CLI that we ship with, the JDBC driver, there's a Python client the community has written, a number of other ones. I think the R client is actually pretty popular too. But basically, the client makes an HTTP request to the coordinator, and the coordinator is the one responsible for planning and then coordinating the execution of the query. And so the first thing it does is parses your SQL query and then comes up with a plan. And that involves a few different stages. The first stage being that you need to come up with a logical plan. So this is, for example, let's go back to that example of doing a join and then a group by. So the plan would be two table scans that go into a join, the join goes into a group by, and that goes to an output operator, which would send the data back to the client. Then we need to do other things like optimization and distributed planning. So in distributed planning, you have to figure out how to execute this query in a distributed cluster. And so that involves things like deciding where the network shuffles need to go. And then optimization is applying a whole bunch of rules to optimize the query, also optimize the expressions inside the query. Once all of that's done, the coordinator distributes the plan to all of the workers. So the plan at that point is broken up into stages, and each stage represents the work that can be done before a network shuffle has to happen. And so the first stage is typically a table scan. So all of the workers in that stage would execute the table scan and then distribute their data to the next stage. I guess in that example query, that would be where the join is happening. And so the coordinator is also responsible for assigning new work to the workers as the query is progressing. And so the coordinator discovers all of the data that needs to be processed, breaks it up into chunks that we call splits, and then assigns them to workers, and the workers process them and communicate with each other to execute the query.
Okay, that was a great high-level explanation. So now I'm going to dive into individual aspects of the explanation that you just gave. So the client starts by submitting the query to the coordinator, as we said, and the coordinator parses and analyzes it. So from a high level, it's just like the client sends a SQL query, and what is the end result of the parsing and analysis phase?
So the end result of the parsing and analysis phase is basically the annotated AST, the abstract syntax tree. So parsing generates the abstract syntax tree, and then analysis annotates the AST, basically to tell you what the types are. So it does all of the analysis of types and looks up functions, so that then it can progress to planning, and the planner will know exactly what types all the columns are, where the tables are located, and things like that.
And while the coordinator is parsing and analyzing the query, the coordinator is also communicating, well, the parser and analyzer, I guess, is communicating with a metadata API. Describe what a metadata API is in this case.
Yeah, exactly. So the metadata API is part of that connector interface that I was telling you about. And so this metadata API describes to the coordinator things like what the types of the columns are in the table and how many columns are in the table. It also describes information like how the table is laid out physically, so whether it's partitioned on particular keys.
So still within the coordination step, after the parsing and analysis has happened, the priority passes to the planning phase, the planner, still within the scope of the coordinator. What are, at a finer grain of detail, what does the planner do with that result of the parsing and analysis of the query?
Right, so the first thing it does is it converts the AST into a plan. And so it does that by analyzing the AST, which has an exact representation of the SQL query, and converting it into plan nodes. So one plan node might be a table scan, and that table scan needs to be matched up to the part of the SQL query that has, for example, the from clause. During the planning, it also decides how to do the distributed planning that I mentioned earlier. And so some of the steps there involve deciding where exactly you need to put the boundaries between stages. And that's important because if you took sort of a naive approach and you made each node its own stage, it would require a lot of network shuffles. So part of that is merging them together and inserting stages in the appropriate places. And this includes things like looking at the metadata API and deciding, oh, this data source already has its data partitioned on a certain key. And so if we're going to do a group by on that same key, then we don't need to do a shuffle to shuffle the data on that key. We can just do it all in the same stage.
After the planning phase, the results of the planner move on to the scheduler. Could you describe what the scheduler does in a finer grain of detail?
Right. So the scheduler is basically responsible for communicating the plan to all of the workers and then assigning them work so that the plan can progress. So the first thing that it does is it assigns all of the tasks for the bottom stage. So a stage consists of tasks, and the tasks basically correspond to a single worker machine. So it will select a certain number of worker machines in your cluster, usually a fairly large number so that you get lots of parallelism, and then it will create one task on each of those workers, and then start assigning splits. And the splits tell the workers specifically what piece of data they're supposed to be scanning. So this, for the HDFS example, would be a specific file. So the worker would go and read that file from HDFS and process the data, doing maybe some filters and projections. The scheduler is then also responsible for coordinating the intermediate stages of the query where the data is shuffled. So it would create an intermediate stage, again selecting some set of machines and creating tasks on them, and then it would tell the bottom stage of the query where it's scanning the data, hey, you need to send your data to this specific machine. And it basically creates all of those connections so that they know where to send their data. It also monitors the progress of the query so that it knows when to assign new splits and when to go look for more splits, and then, of course, monitors when the query has completed.
So in the discussion that we've had between the client and the coordinators and the workers, well, we haven't talked about the workers too much quite yet, but there are three APIs. There's the metadata API that's communicated with the parser and analyzer. There's the data location API that communicates with the scheduler. And then there's the data stream API that is used by each worker. So could you describe and I'll include a diagram of this. There's some great diagrams that I'll include in the show notes. And so each of these APIs is compatible with Hive, internal, Scribe, Puma, and JMX. I guess I'm having a little trouble understanding exactly how these APIs work. So if you could explain the APIs in greater detail and explain their commonalities and what exactly they're doing with Hive, internal, Scribe, Puma, and JMX, I'd appreciate that.
Yeah, sure. So let's start with the metadata API, because that's sort of where everything begins. So in the Hive case, the metadata API, which is responsible for things like communicating to Presto what the list of tables that exist are, and then details about each of those tables. So what columns the table has, what the names of those columns are, what their types are, what columns the data is partitioned on. Those are all things that are implemented in the Hive connector by talking to the metastore. And so the API that provides a list of tables would make a call to the metastore to get the list of tables that exist in the metastore and then return them to Presto. To get more details about a specific table, that's also a call to the metastore. So it would call the metastore, get the description of the table, and then convert it into the objects that Presto interacts with. For a different connector, for example, the Cassandra connector, well, actually, I guess I'm not too familiar with the Cassandra connector, so let's use a different example. But for, say, the MySQL connector. So the MySQL connector is basically just a wrapper layer for a JDBC connection. And so when it wants to list the tables, it submits a query to the MySQL database, just asking for the list of all the tables. And when it wants to describe a table, it again just creates a SQL query that describes the table, submits it to the MySQL database, gets the result back, and converts it into the format that Presto understands. Those other ones work pretty similarly. For example, a proprietary internal data store, let's say you had implemented it as a remote service that uses protocol buffers to communicate. You would implement some sort of API in your proprietary data store that could provide a list of all the tables. And depending on the data store, that list might be a single table. Maybe you want to just view the whole data store as a single table. But you would add a new API to your data store, which Presto could then call remotely and get a list of the tables. And similarly, for describing a table, you would again just add another remote interface that it could call, and then take that protocol buffer data structure and convert it into the structure that Presto understands. So the data location API is the API that tells you where to find the physical data. So in the Hive example, this would involve the name nodes and the metastore. You get the paths that you need to look up, then you walk the name nodes looking for all the files that exist, and then you return those to Presto. We provide a streaming API so you don't have to return every file in a single request, and so it would stream back a list of all of the files so that Presto can then convert those into splits and assign them to the workers. In the example of the MySQL connector, I think it actually just has a single split that it uses. It just says, basically, this is the table that you should query, and those splits, which then end up getting assigned to the data stream API later, know that they can go back to the MySQL database and get that information. And for the example of a proprietary data store, you would need to understand how your data is sharded and which machines have that data. And then you would probably return that list of machines and possibly some paths or other information to Presto, which it could then turn into splits and assign to workers. And then the final one that you asked about was the data stream API.
Yes.
So the data stream API takes those splits, the ones that came from the data location API got converted into splits and were then assigned to workers. And it takes a single split and retrieves the data. So for the example of Hive, it would take that split and take out the file path, and then it would go to HDFS and read the data. For MySQL, it would look at whatever SQL query was in there, submit it to MySQL, and get the results back. Or for your proprietary data store, going back to the protocol buffer example, it would take probably a host name and maybe some parameters, and then it would submit them to your data store, get back the results, and then pass them on to the Presto worker, which would continue processing them.
Are there only communication channels between the coordinator and different workers, or can workers, do they communicate with each other as well?
Yes. So they do communicate with each other, but only in the sense that they fetch data from each other and check to see if tasks have finished. So in each stage, you may need to fetch data from a lower stage. For example, the stage that's processing the join or the group by may need to fetch data from the stage that was doing the table scan. And so in that case, the workers communicate directly with each other to fetch that data. The stage doing the join or the group by also needs to know when the other stage has finished. So
how do the workers communicate with each other?
They communicate using HTTP. All the communication is done with HTTP.
Okay, great. So I want to zoom out a bit. So there's more from the Presto documentation. The documentation says, quote, Presto breaks the false choice between having fast analytics using a expensive commercial solution or using a slow, free solution that requires excessive hardware. So is this saying that Presto is both fast and cheap?
Yeah, I haven't actually heard that quote before. I guess I should read more of our documentation. But yes, that's the idea. So basically, Presto is designed to run on commodity hardware, which is where the cheap part comes from. And it's designed to be fast. That was basically the whole reason for building Presto was that we wanted something that was fast and low latency. And so from the beginning, it was designed to be fast and low latency, and then, of course, to run on commodity hardware. So, yep, you can get both.
And a theme this week has been the migration from batch to streaming. How would you explain the gradient between batch and streaming processes within organizations?
Yeah, I would say that traditionally they've been pretty separate. At least in the companies that I've worked at, you typically do your ETL and maybe nightly reporting in some batch system, such as Hive. And then you have a separate system for streaming. I know that companies like Twitter are using Storm. Here at Facebook, we use Puma. And those have been very distinct systems that may share a data store, but otherwise don't share very much in common.
How does Puma compare to things like Storm or Spark?
I believe it's similar. I haven't worked on the Puma team at all,
Okay,
so
that's
I can't
fine.
compare it directly.
That's fine. Do you know how? Can you describe in any more detail the interactions between your streaming and batch systems? Like, do you have? Is it like you have things that are updating on a regular basis that you consider streaming nodes, and then you run batch jobs across them, or how would you describe it?
Yeah, I would say that generally they're separate systems that feed into shared data stores. So you might use Puma for collecting real-time data, doing some transformation on it, and then storing it into HDFS, where in the future you could use Hive, maybe in a nightly reporting job, to read that data, do some more complicated transformations on it, and then store it into another table or send it out as a report.
Right. So I've heard that the word streaming often gets mixed up with real time. How would you differentiate streaming and real time?
Streaming and real time.
Or are those orthogonal? Or I mean, I hear them used synonymously, but I've also seen criticism of that synonymous usage.
Yeah, I mean, I think that they're both sort of vague terms that can mean a lot of different things. So, yeah, I mean, because you can apply real time to a lot of different systems, even if they're not streaming. Like you could say that the news feed or the ad system that we run is real time because it provides super low latency and you get results back right away. You could also say, though, that Presto is streaming and that the queries are processed in a streaming manner where we never checkpoint anything to disk. But although you could certainly use Presto for pretty close to real-time queries, I wouldn't say that that's related to the streaming nature of it. Like you could use Presto to read your data from HDFS, and that could be like hundreds of terabytes or a petabyte of data. And sure, the query is streaming, but it's definitely not going to run in real time. And the data that you're querying is presumably not being generated in real time.
So you mentioned that that in a streaming, you're not checkpointing to disk at all. Is that to say that a differentiation between streaming and batch is that batch focuses on putting things in disk, or is that not a good correlation to draw?
Yeah, I mean, I guess a distinction that I might make is that batch is designed for very large data transformations, typically that are not time critical, and that need to be fault tolerant. So things like nightly jobs that run, I would consider them batch. Whereas streaming, like in the case of Puma, you have a continuous stream of data that's coming in, and you're processing it to maybe aggregate some particular metric or convert it into a different format and store it somewhere else.
I see. How does Presto compare to HBase?
Presto compared to HBase.
Or are they totally orthogonal?
I would say that HBase is more similar to Cassandra, actually. That HBase is primarily a data store, and I believe it does have an API for making queries, but I don't think it's a SQL API.
Right,
So
okay.
it's really more of a data store rather than a compute engine.
Yeah, see, this is me like learning on the fly during Big Data Week. Um,
Yep.
how would you describe Presto in terms of the cap theorem?
In terms of the cap there,
I mean, once again, I guess cap theorem is typically used to describe data stores, and Presto is not really a data store, so maybe this is not an appropriate question. But I don't know. Maybe you have some interesting thoughts.
yeah, I mean, basically, we are going to have similar guarantees to whatever the data store guarantees. So if the data store does not guarantee consistency, then Presto is not going to have consistency either, because we're reading the data from the data store. If the data store does not guarantee availability, then we're also not going to be available. And this is actually a very real problem that people run into when they're running Presto, is that Presto is dependent on HDFS. And so if HDFS is down, then Presto is also going to be down.
Fascinating. So Presto is written entirely in Java. What are some techniques that are used to gain speed out of your Java Presto code?
Yeah, so we do a whole lot to make sure that things are fast, because of course Presto was basically started because we wanted something that was fast and low latency. And so let's see where to start. So one of the things that we do is we try to use flat data structures. And by flat data structures, I mean that there are a very small number of objects that Presto allocates. So rather than using a data structure that was a list of rows, with each row being one row from your data store, we would instead use a columnar representation where we would store, let's say that your rows were a big int, which was the user ID, so that would be a long in Java, and then a varchar column. So that would be a byte array in Presto, because it's a varchar. So rather than storing those as rows that contained a long and a byte array, we would instead columnize them. So we would have a single array of longs, and then we would have a single array of all the bytes, and then an array of the offsets or length, so that you knew which bytes made up each row. And the reason that we do this is to avoid GC pressure. It's much more efficient to have a single array of longs than to have a list of objects and have longs inside those objects, because every object has overhead, and it also will then need to be garbage collected, and it creates a whole bunch of references, and this makes the garbage collection more expensive. So that's one of the things we do.
Another thing is, I think loops are directly converted to bytecode. Could you explain that?
Yeah, so one of the things that we do is for all of the SQL expressions. So for example, let's say that you selected some mathematical transformation. You had some data and you wanted to compute the sign multiplied by 5, let's say. So that SQL expression, sign of x times 5, would be compiled into bytecode and loaded as a completely new Java class. And the reason that we do that is for performance. That by converting it into bytecode, the VM can then do much better optimizations on it, and it's much faster than having some sort of interpreter in Presto that interprets these SQL expressions. Um, yeah, and there are a number of other places that we compile things into bytecode. For example, the way that aggregation functions are written is that you write them as a class that has a bunch of static methods, and then there's a compiler that analyzes that class, all the static methods and the annotations on those methods, and then generates a new class that implements all of the sort of boilerplate code and loops. So I think that's where the reference to loops came from. And it will then load that new class. This all happens on the workers, and will then aggregate the actual data.
So Presto is 4 to 7 times more CPU efficient than Hive, and 8 to 10 times faster than Hive. Other than what we've already discussed, are there any things you have to mention about how you achieved these improvements?
Yeah, so a lot of the CPU efficiency comes from not doing the checkpointing and using flat data structures instead. It also comes from the fact that Presto was designed just to be a distributed SQL query engine, whereas Hive is built on top of MapReduce, and so Hive is fitting itself into a more generic framework. So we can do, or we have done, more optimization to make it efficient. Let's see, as far as low latency, I can't think of anything else right now to mention about why we're lower latency than Hive is.
Do you know what the benchmarks that were used to take a look at that efficiency and the speed improvements?
I don't know specifically about that one.
Okay.
I know that there have been a number of benchmarks that were comparing Presto and Impala and Hive. And the result was that Presto and Impala, I think, were pretty similar, and both of them were more efficient than Hive. That work, I think, was done by Cloudera, but I don't remember for sure.
So there's a 2013 talk from Martin Traverso that I'll include in the show notes. He said that 60% of Presto's time is spent converting data from HDFS format to a format that's consumable to the client. Could you describe this this conversion process in a little more detail? I think you've touched on it already, but maybe you could discuss it in more detail.
Yeah, I don't know specifically what he was referring to, but I assume what he was referring to is the time spent reading the data from HDFS and then converting it into the internal data structures that Presto uses. And so when that happens, basically you do a remote read from HDFS and you get back some bytes that are in whatever file format the Hive table was stored in. And so in some cases, that may just be plain text, which then needs to be converted into those arrays of longs or arrays of bytes, whatever columnar data structures Presto uses. And that we found can be very expensive. For one thing, doing a remote read like that is expensive, but then also doing the conversion from Hive's format into the data structures that Presto understands is expensive. And one thing that we're working on there is we're actually building a new data store called Raptor, which uses local disk and is very closely designed with Presto so that it will be much more efficient at doing these reads, that rather than doing a remote read, you're reading from local disk. And we're also planning to make the file format much more closely integrated with Presto so that the decoding would be faster.
Can you describe that project in more detail?
Yeah, sure. So it's all open source. It's in the.
You said it's called Raptor?
It's called Raptor. Yep. Yeah, it's in the Presto Raptor directory. I have only done a little bit of work on that project. Our team members, David and Nalima, are doing most of that work. But basically, the idea is to build a data store that runs co-located with the Presto workers and is very closely integrated with Presto. And so the way it works is it stores all of its data on local disk. in a similar way to the HDFS data nodes, but then for backup purposes, we would use a separate system. For example, HDFS or a Gluster file system. And so right now we don't have any of the complexity of doing replication inside Raptor. It's basically just there to store the data and make it efficient for Presto to access, and then use something else for the backups. It also keeps a lot of metadata, which allows us to do more efficient scans. For example, if you wrote the data and let's say you had a column of event times, the statistics for that column would be collected, and assuming your data is coming in every hour or day or some regular interval, it's going to naturally end up sorted. And so we can then prune a lot of the data and skip reading it.
Okay, that's really interesting. So in that 2013 talk that Martin Traverso gave, he also said that the roadmap for Presto included performance optimizations, the ability to do big joins and aggregations, and more functionality that Hive does well. So have those improvements been made since 2013, and what other sorts of improvements have been made?
Yeah, we have made an enormous number of improvements since 2013. So on the performance side, one of the big things we did is we wrote a completely new reader for the org file format. So before that, we were using the Hive code, which was designed to work well with Hive, but which didn't work as well for Presto, primarily because of those conversions between the data structures that Hive uses and the data structures that Presto uses. And there is a blog post that we published. I've actually forgotten when it was published, but in the last 6 to 9 months, I think, that talks about that work in much more detail. But that was a huge performance gain. As far as bigger joins and aggregations, that was actually something that I worked on. And so I can go into a fair bit of detail there.
Yeah, please do.
Yeah, back in 2013, one of the big limitations of Presto was that you really could not do any joins or aggregations that had cardinality bigger than, I don't know, a few gigabytes or maybe a few tens of gigabytes, depending on how much memory your workers had. And the reason for that was just the way that the distributed planner worked. It was fairly primitive at the time, and so it always planned all joins as broadcast joins. So that's where you take one side of the table, you broadcast one copy of it to every worker that's going to process the join. Each of those workers takes the copy of the table, builds a hash table out of it, and then uses that hash table to match the incoming keys from the other side of the join. What this means, though, is that because every worker needs to have a complete copy of one of the tables involved in the join, you can't do a join where both sides are bigger than the available memory on a single worker. So if you wanted to join one table with a terabyte of data to another table with a terabyte of data, it's never going to work. And so the first step was changing it to hash distribute both tables on the same hash function, and then have each worker only get a slice of the table on the right-hand side of the join. That's the one that's always turned into a hash table. So it gets one shard of that table, builds it into a hash table, and then you have as much available memory as you have in the sum of your workers. Then that brought up a number of other issues around how we manage memory. So back in 2013, we had a very naive way of managing resources in Presto, the primary resource being memory. And basically the way it worked is that each worker for each task that it was processing, for example, building one of those hash tables, it would have a limit on the amount of memory. And I think back then the default configuration was 256 megabytes. You could increase that a little bit, up to a few gigs probably, maybe even 10 gigs if you had a lot of memory on your machine. But the danger was that there was no global view of how much memory was being used. And so if, say, 50 people all submit queries that are doing some sort of join and therefore are building hash tables that remain in memory, it was very easy to run out of Java heap space. And so what I worked on was a cluster-wide resource manager. And so now the coordinator has a centralized view of how much memory is being used on every worker, and also on every worker, it has a local view of how much memory every query that it's processing is using. And if you get into a situation where one of the workers predicts that it's going to run out of Java heap space soon, it will start pausing some of the queries. And then the coordinator will make a centralized decision about which queries should continue running.
Cool. Okay, so it sounds like you have made a lot of improvements since 2013. That sounds like a ton of work.
Yeah. Yeah, there's been a ton of other features that have been added too. I think we now pretty much have feature parity with Hive. I don't think there are any major features that are missing. I know another one that we were missing back in 2013 was the lateral view functionality, which allows you to um, basically take an array or a map and convert it into multiple columns, which you could then query separately by it takes the array and converts it into a column containing the entries of the array, or a map and converts it into two columns of the keys and the values. So we now support that using unnest, and we added a lot of other features.
Do you have any awareness into how Airbnb and Dropbox or you said Netflix, other companies are using Presto?
Yeah, so certainly not in a lot of detail, but I talk to the Netflix guys pretty regularly, and I've seen their presentations on how they're using it. And it sounds pretty similar to the way we use it here, which is they use it for a lot of ad hoc queries. They, of course, have all of their data stored in S3 and other stores in AWS, and so they run Presto in AWS rather than their own data centers like Presto or like Facebook does. And then they've got it integrated into a bunch of their other analytics tools, which I forget the name of now, but I believe there are some slides floating around on the internet from a presentation they gave. But their analysts and other engineers can then use it for making interactive queries.
Is Presto under the Apache project?
No, it is not. It is Apache licensed, but it's not an Apache project.
Okay, why did you choose to put like Cassandra? Cassandra is under Apache, for example, but Presto is not.
Right. I mean, I think it may be something that we reevaluate in the future, but at least for the moment, we feel that it's more important to just focus on the code base, and we think we can move faster by just having it as a separate project rather than making it part of the Apache project.
Is the political situation any different if you are under Apache versus just under Facebook open source?
Um, yeah, I guess I'm not super familiar with how Apache
or like
projects
how
are
does
run.
maybe I should say management, not I didn't mean in terms of like politics. I meant just more in terms of like because you said you can move if you can move faster under Facebook. I'm curious, what are the properties of being under Facebook open source versus being under Apache open source?
Yeah, well, so I mean, obviously, being under Facebook open source means that uh, we control the project and, of course, work with the community to integrate their needs. But it means that we have more control over the project than would be the case with Apache. Also, Apache, I believe, has an incubator process that you have to go through, after which point you sort of graduate into a full Apache project. And so there's sort of a process that needs to be gone through to become an official Apache project. Um, and so we, at least for now, have chosen to focus just on developing the code base rather than going through any of those formal processes.
Interesting. Could you give me any more insight into the management process within Presto? Like I'm always curious about how different types of engineering teams are managed in different ways. Presto is a pretty unique project, so I'm wondering if there are any unique engineering practices that go along with it.
Yeah, let's see. I would say that one of the things that distinguishes it from other large projects that I've worked on is that it is a very small team. So we only have 8 software engineers, and then we have 1 production engineer who helps with production deployments and managing all the clusters and monitoring them and things like that. But the team itself is very small. There's only 8 software engineers, and pretty much everyone is very experienced. I would guess that the average experience level on the team is probably 5+ years of experience in the industry. So it's primarily experienced engineers and a small team. Obviously we have a manager for the team, but since everyone is pretty senior, a lot of it is the team self-organizing itself and identifying what impactful work needs to be done. So I think that distinguishes us a bit from other teams that I've been a part of.
In that self-organizing sense, are you saying that you don't? There's not as much. How does issue tracking happen? Like, is it just? Do you just pick up How does issue tracking happen?
So we use GitHub for all of our issue tracking, which makes it very easy to work with the community because they can report issues and they can see the issues that we've reported. Typically, because the team is so small, people know who it is that is likely to be an expert in that issue. So if I were, for example, to discover a problem in the Raptor code base, I know that David and Malima are the ones that work on that part of the code base, so I would assign it to one of them. And because we're a small team, we talk very regularly. The team pretty much all goes to lunch together. Many of us have breakfast together. And so there's just a lot of interaction between all the team members. And so if an issue comes up, you'll probably be talking to that person in an hour or two anyway. And so a lot of communication just happens offline like that.
Interesting. So to begin to close off, what is the future of Presto?
The future of Presto. Well, that's always hard to predict, but I would say there is a lot more work to be done around adapting execution plans at runtime. So right now, the planning process that I walked you through involves coming up with a static plan. So the user submits a query, the planner decides how to execute it, it starts sending it out to the workers, and the workers execute on that plan. I think one of the major wins for Presto in the future is going to be coming up with a plan, sending it out to the workers, having the workers start executing it, but then possibly discovering that the data is highly skewed, or that the data is higher cardinality than you expected, or maybe it's lower cardinality. And then adjusting the plan to take into account that new information that you have. And this, I think, will allow Presto to make a lot of optimizations that are not possible today, in a similar way that traditional SQL databases use stats. So right now, Presto doesn't use any stats. And because of that, we don't do things like join ordering that a traditional database would do. And part of that is because we have a hard time collecting stats unless that metadata API that we talked about were to provide them. But at the same time, we don't want to push a whole lot of complexity into that interface, because that would mean that everyone building every proprietary data store would also have to keep those stats themselves and provide them to Presto. But by doing that adaptation at runtime, you can basically observe, okay, this is the statistics of the data that I have observed, so I'm going to change my query plan and execute it in a different way.
So what else would you like to add about the Presto project and about engineering at Facebook?
Beyond that, I basically see Presto just taking on more and more work and being used more broadly in the industry. Like Teradata just announced that they were going to start supporting Presto this summer, and so they have a large engineering team that's contributing to Presto. And I imagine that will move us into a lot of more traditional enterprise companies where Presto hasn't been used as much right now.
I meant to ask about this, but do people use like Tableau or something as the front end to Presto, or does Presto have its own front end that is meant to be used with it?
Yeah, so the only front end that Presto ships with is the CLI. And so, yeah, using Tableau is a very common case, particularly for business people and analysts who may not be as familiar with a command line interface.
Cool. Well, Christopher Berner, thanks for coming on to Software Engineering Daily. It's been a real pleasure talking to you about Presto. And yeah, so I'm a big fan of what you guys are doing, and thanks again.
Cool. Well, thanks so much. Likewise, it was a pleasure.